Good to do.
Okay. Okay, thank you very much. So I think it's a long day, and I think everyone is. Thank you very much for inviting me here, and everyone here to my presentation. So I think my presentation is quite easy. I think we have a lot of very good presentations for this day, and for my presentation, just some animation, so everyone should be relaxed and enjoy that. Okay, so I'm talking about how we simulate the city-scale disasters with physics-based methodology or AI-based methodology. So this is online on my presentation. So firstly, why we do the work, and we firstly begin from earthquake, because I think many of people here are similar to me that were firstly working on earthquake, and then we extend it to different disasters, and then we introduce some AI-based method to our research, and finally come to the conclusion. So this is the background. So our working on the cities, and the city have a lot of disaster. We are facing on not only natural disaster, but also like the COVID, that is a very severe public safety problem. And we want to simulate the impact of the disaster to the city. We not only want our simulation to be accurate because we are scientific research, we want the research to be efficient because we always have time and resource limitation. And another important thing is that we want to make our simulation realistic. Why? Because when we are working on the city problem, we are always working with the administration, the people from different disciplines, and they don't know what actually we are talking about. So we want to make some very interesting animation to make them know what the disaster come and what will happen to the city. Okay, and we are facing the problem, particularly for China, that in China, firstly, we don't have a very strong earthquake in the densely population area for nearly 50 years. So we don't know how about to set up the model for these modern Chinese cities. And also China constructed a lot of new buildings, and these new buildings don't have sufficient earthquake data to develop some empirical model. So we are going back to try to develop some physics-based model. I see Professor Horry here that maybe we have the common idea that the physics-based model can set up free from the limitation of this empirical disaster data. So for example, no matter what kind of structure you have, new structure or old structure, we all follows the no structural dynamics. And then also no matter what kind of wind you have, you still have to follow the fluid dynamics so that we can use this physics-based model set to study the disaster. And also when we have this physical disaster, we have some limitation. For example, we need to connect the data. It's very time consuming. We need to set up the model, or we do the computation. It's all very time consuming job. So we can use our AI technology to accelerate the modeling or simulation job. So that is the background of my research. So firstly, I'm coming out talking about the time history analysis for earthquake, not only for single building, but go to the city scale. So we begin from the building scale, and we can see that no matter you are talking about a single building or 1,000 building in a city, all these buildings follow the structural dynamics. So we can do the nonlinear time history analysis. We input the dynamic ground motion, we solve the dynamic equation, and we can get response either to a city or to a building. Okay, so first we begin from the buildings. I think we did this job about 20 years ago. At that time, China are constructing a lot of super tall building. And this building is so tall and the components so big, and the seismic intensity is so high, so it is a very challenging problem for people to do the design. So we are thinking about, okay, so we are doing this kind of tall building. So what kind of purpose? We do the structural analysis, and we believe that there's two important things. First is that we need our numerical model can analyze the real world complicated structure. Some numerical models are very good, but it's good for the experimental components. But we go to real world structure, we need our numerical model to adapt to this real world very complicated building. The second is that our model can simulate to the collapse behavior, because this is very important for the safety of the buildings. So we propose that we can, based on the material constitutive law, we use fiber beam element and a multi-layer shear element to set up the finite element model for this super tall building. And with this model, for example, this is one of the tallest building in China. that we can use this fiber beam element model and multi-layer shear element model to simulate the collapse behavior of this entire building. We did this job, I think, in 2019, 2010. Okay, so when we do the simulation, we not only do some animation. I think that animation, the Hollywood made much better than me. We want to use this simulation for the design purpose of these buildings. So then we go to another tall building. It is a construction in Beijing. The height of the building is higher than 500 meters, and the seismic design intensity is about twice of that one in Shanghai. So we work together with the design institute. We begin from the selection of the structural scheme, and then to the design some key parameters and key components. And we spend about 4 years use our collapse simulation technology for this real-world tall building. Okay, so this is the original the structural scheme of this tall building. So we can see that this building, on the bottom of this building, they have the mega braces, and the engineer removed the mega brace for the upper 4 zones of the building. So you can see that is obviously an interaction between the different structural systems, and this kind of structural system at the middle of the tall building will induce some discontinuity of stiffness and stress. So it's very bad for the performance of structure subject to earthquake. So then we optimize the structural design. You can see that finally we have the mega brace from bottom to the top. So with this Foley brace scheme, we can not only increase the collapse margin ratio of the building about 15%, but also can save the material about 11%. So you can see that that can improve the structural performance quite well, and the design agency like the optimization very well. And also we can optimize the design of some critical component. For example, following our simulation, we found that at the zone 6 of this tall building, it is a very critical part may induce the collapse of the entire structure. So we can embed some steel braces in the shear wall, and this shear wall with only about 0.1% of the total steel consumption of this tall building, but it can increase the collapse margin ratio of the building to more than 12%. So this is a very efficient way to increase the safety of the tall building. Okay, so this is the one for the single building, and then we can use same idea. We use the nonlinear time history analysis from one building to the entire city scale. So if we can do the nonlinear time history analysis of the entire city, then we can accurately represent the behavior of different buildings and also the features of different earthquakes. Okay, so then we, for the different kind of buildings in the city, we propose different structural models. So for some conventional buildings, we propose the moderate fidelity model, that is MDF model. For example, we can use MDF shear model for the multi-story buildings, and use this MDF flexural shear coupled model for the tall buildings. Of course, if you have some special buildings, we can use the high fidelity models with refined element map model to simulate these very special ones. And then for this conventional building, because we have thousands of such buildings in a city, we cannot generate the structure model one by one from design drawing. So we proposed a method to determine the parameter of this interstory behavior of the MDF model. For example, from empirical models, we can predict the interstory stiffness. We can, from the design code, to predict the design strength of the interstory behavior, and we can connect a lot of test data to predict the actual strength and the actual ductility of this MDF model. So with this model, both the high fidelity model and the MDF model, we can use it to simulate very complicated city building and clusters. So for example, this is the tall building clusters in Beijing CBD area, and we input the historical 1679 MH Sanhepinggu earthquake. We can clearly show the shaking of the tall building, and in additionally, we can not only see the shaking of the tall building, but also we can see different color represent the damage on different story of the building. So we can know the damage on each story of sheer building at each moment. And for example, for these 3 buildings, with the photos here, we use a high fidelity model for that. And for other conventional tall buildings, we use MD model for that. Okay. And then we can further combine the dynamic model of buildings with the finite element model with the soil beneath that. For example, we have some buildings, very dense building like this one in Hong Kong, that with very dense site, and there was some interaction between the building and the site. So we can build a finite element model and shaking the soil and the building together. Okay, this is people call it the site-city interaction. So this is one example. So it is the Beichan city is constructed on a mountain area. So we input the ground motion. We can see that at that time, we can not only simulate the shaking of the building, but also we can see the shaking of the mountain. So we can clearly see that the ground motion on the top of the mountain will be higher than the one on the feet of the mountain. So this is, we can call the terrain effect of this site. And also another interesting case is that we can simulate discuss the behavior of tall buildings, super tall buildings in a dense city area. This is what we did for the Beijing CBD area. We firstly connected the CBD area, and then we can do the simulation. So on the left is the earthquake we simulated, and on the right is we simulate the shaking both of the building and also the soil beneath the building. And the contour on the right figure is the the stress wave generated by the reaction force of the tall building. So we all know the the third principle of Newton's law. So we have the force equal to the reaction force equal to the force. So if we have the earthquake so strong to shaking the building with several hundred meters tall, the actual reaction force will also equal to the force, seismic force, to the tall building. And this reaction force will generate a stress wave to about several hundred meters, and it will bring additional damage to the short buildings near to the tall building. So you have a short building near to the tall building, the reaction force may be induced additional damage to these buildings. And also we have this city scale nonlinear time history analysis, and we are very worried about the resilience. So we can combine this dynamic simulation result with the resilience performance indicators, so we can predict the seismic induced damage to, and also the repair time to not only single building, but the entire building clusters. For example, firstly, we can do it from single building. So we can combine the building information model together like some resilience code like FEMA P58. So we can clearly know the damage to different components, and we can go inside to say, okay, which building, which damage how much damage to the different component, how long time it will be repaired. And then we can do it further to the entire city scale. So this is the entire Beijing city. So we generate an earthquake on the east suburban of the Beijing city, and we can simulate the recovery process of the entire city after earthquake. You can see on the right, the animation shows that how the distribution of the labor force in the city. Because after earthquake, there will be a damage to the entire city, and there will be thousands of buildings need to be repaired. So how you distribute the labor force to make the city have the best recovery process, that we can do that kind of simulation. So this is a typical case, interesting case. And this simulation, we can not only use it for the research purpose, but we can use it for the real-world application, not only for the pre-earthquake planning, city planning, but also can use it for the after-earthquake emergency response. So this is a typical case. We work together with the same center of the United States. So the UC Berkeley connected the 1.8 million buildings in the San Francisco Bay Area, and then they simulate the ground motion of a whole magnitude of 7 earthquake to the entire earthquake area. So we input the ground motion to each of these 1.8 million buildings. Then we can simulate the shaking of the entire San Francisco Bay Area. And we can not only see the shaking, but also we can see the seismic induced loss to different buildings, and also see calculate the repair time of different buildings. So we can get a better view of the entire resilience of this city area. And also we can use it for some interesting secondary disaster. This is a typical case. For example, this is for the falling debris in the earthquake. So on the left is a video taken from Mexico City. You can see the building is okay, but there's a event falling down and may kill people. And on the right, this is the animation taken in Japan after the Tohoku earthquake. People are running out of the building, but the falling debris falling down, it will induce damage. But how to calculate such a behavior of the falling debris? It is a very big problem, and there's no good method to do that. But with our city-scale time heat analysis, we can do it very easily. So first we do the simulation, we can know the shaking of different buildings. And then we do some experiment, we can know how much damage of this to different evaporable walls or the glass curtains. And we can also know the distribution of the falling debris on the ground. Then we can use let the student to do some experiment to know how much debris distribution to the movement of the people. Then we can give the evacuation simulation to predict the damage to the area. So this is a typical case. We do it for the Beijing CBD area. So we have the earthquake. The building is still standing there, but you can see that the red dot means the falling debris. And falling debris will affect the evacuation process of this area. And we can see that on the top, you can see that we use this falling debris. We can know how much area will be covered by this falling debris. And then we can set up a better sheltering place or better evacuation routine. And on the bottom is that we can do the evacuation simulation based on this falling debris. We can see that with this falling debris, the evacuation time for the area is much longer. The time cost to the evacuation is much longer without this falling debris. And we can also use this technology for the pre-earthquake urban planning. We use it for about 26 provinces in China and in more than 50 cities. And this is one of the example that we use this technology for the disaster preparation for the 2028 Beijing Winter Olympics. And we get a very good feedback from this Olympic organization community. We simulated the entire Olympic campus and do some preparation for the disaster if the earthquake happens during the Olympic times. And we can also use this technology for the the emergency response after earthquake. So on the left is the conventional method we were doing for the earthquake damage assessment after earthquake. So we have the earthquake magnitude, and then we use some ground motion prediction equation to predict the intensity, and then we use fragility curve to predict the loss. But the entire routine has significant uncertainty. But with our technology, we can directly use the recorded ground motion, and we input the entire recorded ground motion to the city model and do the nonlinear time history analysis, so can significantly reduce the uncertainty. Okay, so we developed a program called REDACT, Real-Time Earthquake Damage Assessment, using city-scale time history analysis. So every time somewhere have earthquake occurred, we get the ground motion, we put the ground motion into our building inventory, and we can predict the seismic damage. You can see that this is a real earthquake in China. The different circle represent different station. The different color in the circle represent different damage ratio. The red dot means the epicenter of the earthquake, and the background of blue contour means the population distribution density of the area. So we can clearly see how much damage to the area and how much damage to the density population area. And this is one of the typical example. In 2017, there is a magnitude of 7 earthquake occurred in China. So some agencies use the conventional way to predict this earthquake and said, okay, there will be tens of thousands buildings will collapse. So when this report submit to the central government, this raise a very big alert. So because there will be a very severe consequence. And at the same time, we also use our method to the prediction and say, okay, this way earthquake will have a very small possibility of building collapse. So you can see this two totally different result after the earthquake. One agency said, okay, there will be tens of thousands of buildings will collapse. And we said, okay, there are very small possibility of collapse. So at that time, that we have a lot of debate which one will be correct. And after 1 month, there is a site investigation report. So there's totally about 73,000 buildings are damaged, but only 6 buildings collapsed. So our result is quite well with the actual damage. So that we get a lot of credit from this event. So we use our time every time for the earthquake. We not use it for some domestic earthquake, but also use some earthquake, particularly for earthquake in Japan, because Japan have a lot of earthquake and data sharing is very good. So it's a very good platform to update, improve our program. So it's very important. And here is some typical example. For example, this the first figure is what we do for the Anchorage earthquake in Alaska in 2018, just quickly after earthquake. And in the middle is the earthquake for the South California. And on the right one is what we did for the Fukushima earthquake in 2021. So I think you can clearly see that the prediction result is very interesting ones. Yeah. And then when we did it for earthquake, we can further want to extend our research not only for earthquake, but also for some other disasters. So we can see that we are, when we're working together with some administration, we found we're facing 2 challenges. The first challenge is that if you're talking to, for example, a city government, they are not only worried about one disaster, they are worried about different hazards. So do we need, for example, a system for wind, another system for earthquake, another system for fire? It is not reasonable. The second one is that they are worried about not only the total area, but also some very important buildings. So they are worried about not both the macro scale and also the micro scale problems. So we can say, okay, maybe we can build we call it a city information model that we combine the GIS model and the building information model together. So the GIS model for the entire area and the building information model for some critical buildings. And then we input these different hazards into this city information model, and it can be used serving for different purpose. So we can use this same model as a common platform for different hazards. Okay, so firstly, we begin from our Tsinghua University campus. So we set up the city information model for the entire campus, and also the building information model for some very special buildings. And then we have the unified data format. So no matter you worry about the regional scale or building scale, or no matter what kind of disaster you are worried about, earthquake, fire, wind, or COVID, you can still use this numerical model to do some simulation and management. Okay, and there is some details about what we did with hazards in addition to earthquake. For example, the fire and the fire following earthquake. Because firstly, our fire model is also a physics-based model. And secondly, because our model all the models are physics-based models, so we can very easily connect the different models to each other. So we can do it, firstly, we do the earthquake simulation, and then we connect it to our fire model. We can do the fire following earthquake simulation. Okay, so this is the work we did in 2016. So we can, because we are using the physics-based model, so we can not only simulate the fire expansion, but also simulate the smoke in earthquake. So this is, at that time, we don't have a good case. We can just show, okay, on the right is the fire following earthquake in after Kobe earthquake, and this is on the left is our simulation. It looks similar to each other. And then we are lucky that there's this morning said about a Noto earthquake last year. So on the left is our simulated burning area, and on the right is our simulated burning area with the actual burning area. So we found actually they are quite close to each other. The important thing how we can do the simulation is that because we are physics-based models, so we can put the weather condition into that, so we can make the simulation much better. And this technology also used for the real-world case. So this is what we are planning for the second administration of the Beijing city. So on the top is the original plan. And we show this result to the city government. They quickly found, okay, this plan is very terrible because the fire area is very close to the office of the mayor. So they revised the plan and move all these risk buildings to far away from the center of this emergency center. So you can see that this realistic animation can make the communication between the administration and the site much easier. And also we can do it for wind. Traditionally, people use this empirical model for the wind. So we can combine the city scale structure analysis with the city scale large eddy simulation. So we can use it to simulate the wind-induced shaking of the tall building in the city area. So here is the case. This is the tall building in the downtown area of San Francisco, and we generate the CFD model of this area. Of course, we validate our model with some wind tunnel test. And here we can see that the wind goes through the building. We can clearly see how the wind goes through these different buildings, and under this time-changing wind pressure, we can clearly see the shaking of the building. We can see two interesting things. First, on the left, we can see that because the overlap of different buildings, the actual wind force on the building is quite different with the design code. And on the right, we can see that actually the shaking of the building subject to this wind-induced wind force is quite different from the Gauss distribution in our design code. And we can not only use for fire wind, we can use for some new hazards like the COVID. So in January 2020, maybe you have a memory that just the breakout of this COVID, so China began to build some temporary hospital, and the entire construct time for this hospital is only for 10 days. So in all those days that we don't have the time to predict the virus in the harmful air in this hospital. So we use our technology I mentioned before to do the thing. You can see that we use only about 6 hours to finish the simulation of the exhaust harmful air from this hospital. And this is all the hospital we served during the January and February. The total bed using our technique is more than 10,000, and we can reduce the risk of harmful air to about 50 to 90%. So we get a very good feedback from the users. Okay, so this is a summary for the case. We use the San Francisco city as an example. So we can use the same data form. We can use the physics-based model not only for earthquake, but also for wind and for the fire. And then we move forward that we want to bring the AI-based model to further improve our modeling and simulation. The firstly, we are talking about how to get the data for the city, because we have thousands of buildings in a city and even millions of windows in a city. So if we count the buildings and the windows one by one, it is almost impossible. So we can use the AI to help us to set up the building model and also these window models. So firstly, we begin from the UAV, because the drone fly of the city is quite a convenient way to connect the data. But after the fly of the drone, how we know the different location of building or different location of trees? So that is the first challenge we are facing. So we use this new technology, combine the deep level V3 and PointNet++. So deep-net V3 is good to 2D problem because they have the color information. And PointNet++ is good for 3D problem because they have the 3D coordination. So we combine them so we can identify the building and the trees with very high accuracy. So we can set up the city model within minutes, including trees, road, and buildings. But in some of the city or some of area, we don't have the permission to fly drones in that area. So we select another method to generate the city model, so we can use the street view image like the Google Earth to generate this city model. That we download the street view image from this internet platform, and then we use AI to identify the building, and we use the coordination of the image and the coordination of the GIS-map to predict the dimension of these buildings. Then we can generate the model of the city. So that is what we do the job. So first we get the street view image, then we use AI to identify this building, and then we do some coordination calculation to know the actual dimension, actual location of the building. And with this technology, we can generate a building automatically in about 1.4 seconds, and then we can generate an entire city very quickly without go to the local site. And also sometimes working on wind, we know how many windows we have. And if we have a drone to fly over the area, then we can use the drone to take the photo of the buildings and then use AI to identify to recognize the windows on the wall, and then we can generate the model to predict the wind-induced damage to the windows. So here is the example. So we have this photo on the building facade, and then we can recognize the windows, and then we can do the prediction, and we can see that we can make the process much more efficient and also very accurate. But also we have the problem in some cases we cannot have this permission to fly drones. So we can still use the street view image to do the job. But when we have a street view job, you can see that there are always some trees or other objects to block the view of the windows. So we have different view image, and we combine them together to recognize each window on the facade. And then with this technology, we can predict, okay, if a typhoon comes, how much damage to this wind in a city area. And also another thing is that when we have a disaster, we want to know how much shaking of the building to that disaster. And in many cases, we don't have this instrument installed on the building. So we think, okay, maybe we can use these surveillance cameras to tell us how much displacement of the building. But this kind of cameras, they have the limitation. Firstly is that they don't have a target mark on the building. So we need to identify the movement without the target mark. The second is that we want to know the three-dimensional movement, but we always have only one camera. So how we know the three-dimensional movement with only one camera? And finally, this camera always have insufficient resolution. So how we increase the resolution of these photos? Okay, so firstly, we propose that we can use the target-free method to predict to identify the movement of the structure. So here is the example. Okay, move. Oh, it's moving. Okay, it's moving. Yeah, you can see that if we have different cameras, even we don't have a mask on this building, we can also identify the movement, three-dimensional movement of this test specimen. And then if we have only one camera, how we know the three-dimensional movement? But you can see that this is a very famous e-defense animation. You can see that when we see the film, we know how much three-dimensional information of this building. Even we just have one video. Why? Because we have brain. We can use our brain to identify the three-dimensional movement. So if we use the similar technology, we use the deep learning to do the job, then we can know the three-dimensional movement with only one camera. So here is the fundamental idea. So we firstly build up the target object, target building, the three-dimensional model, and then we train the AI with this people-generated three-dimensional model. And then if we have a photo, we can quickly rebuild the pose, the actual location of this building with this deep learning technology. Okay, so here is the example. You can see that we're shaking this very simple roof model, and we use only one camera to look at it. But then with this deep learning, with the right to figure, we can clearly see the three-dimensional pose of these objects. And then with this three-dimensional pose, we can know the three-dimensional movement of these objects. And then the final problem, as I mentioned, that we don't have sufficient resolution for these figures. But now with deep learning-based super resolution, we can convert a low-resolution image to a high-resolution image. So we can also use this technology to increase the resolution of the surveyed camera image. So you can say the fundamental idea is that we have both the high-resolution image and low-resolution image. And then we train the AI, and then the AI can translate a low-resolution image to a high-resolution image. So here is the example. You can see that you have this low-resolution image here, and after the super resolution, we can transmode it to a high-resolution one, and you can clearly see that the photo quality is increased quite a lot, and the error identified from this image is reduced quite a lot. Okay, so all these technologies combined, we combine them together, use it in a real-world case. So this is a real-world tall building in China. It is shaking very strangely in 2021. The height of the building is more than 300 meters. So people want to know why the building have such shaking, but we don't have this health monitoring data to know that. We only have a surveillance camera to know this shaking. So we firstly use this camera data to generate the three-dimensional movement. We can use our technology to generate the three-dimensional movement, but because the resolution of the picture is not good enough, so we have some shift on the right. You can say some shift in the resolution result. So then we have our super resolution method to increase the quality of the resolution of the image. And with this high resolution image, we can clearly get the three-dimensional movement of the building. And it will be very helpful to identify the reason of the shaking of the building on that day. And even after the disaster, during or after disaster, we can use this technology, for example, to predict the ground motion input or to predict the damage to the structure. For example, we want to know the ground motion to in an earthquake. And we can find that actually that we have three different tasks to predict ground motion. So before earthquake, we always to say, okay, we have a magnitude 7 earthquake, what kind of ground motion we have. And during earthquake, we have early warning. What means we have for example, we have 3 seconds of ground motion. We want to predict the ground motion of the entire 30 seconds. And after earthquake, we have some stations have the entire ground motion record. But we also have many sites, we don't have the station. So we have these three kind of tasks we are facing every day. But if you're looking at that, you can find actually these three types have some common case. For example, you compare the case 1 and case B. You can see that, okay, for case 1, the earthquake is assumed earthquake. For case B, you have a real earthquake, but you don't have the foreground motion. And for case B and case C, for case B, you have only 3 second ground motion. And for the case C, you have the entire ground motion, but you want to predict some unknown location ground motion. So you can combine them together to propose a new method to predict do the ground motion prediction job. So this is we call it a mask transform for these three tasks. So for the case 1, before earthquake, you mask everything. You assume a earthquake magnitude and predict all the ground motion. And for task B, you have the earthquake. You have the 3 seconds of ground motion. You know that. And then use this one to predict the left 30 seconds of ground motion. And for task C, you know all the epicenter earthquake and the ground motion. You predict some other location. So you can combine them together to generate, and we call it a quick transfer to do the ground motion prediction. And here is a typical case example. You can see that for both the forecast, ground motion forecast case and early warning case and interpolation case, our model are all better than existing models. You can download the paper from this archive on the bottom. And also that after earthquake, we want to predict the seismic damage to different area. We have Fujita model, we have the capacity spectrum model. They are very efficient, but they are not accurate enough. Time analysis is accurate, but it's very time consuming. And how we combine these advantages together? We can see that, okay, we have the phase recognition that we see the phase, we know, okay, this is Professor Horry or someone else. And we can also do the similar thing. We can transform the ground motion to a, for example, wavelet figure or time frequency distribution. So each ground motion have each wavelet image. So you look at the wavelet image, you know what kind of ground motion you have, and then you can use this technology to predict the structural response. So this is what we do. We transform the ground motions into this wavelet flags and image, and then we use the CN to identify different earthquakes. So here is the result. So we have an earthquake, we transform each ground motion, we transform to the wavelet image, and we use the wavelet image, which will predict the structural damage. So we can reduce the error to about 61%, and also increase the time efficiency to more than 1,500 times. So it's a very accurate and a very efficient way. Okay, so final conclusion that we are moving from a conventional method to a physics-based method. So we have better accuracy and more realistic result to the users. And we can use the city information model to predict a better data model to set up the simulation. And we can use the AI to make the simulation more efficient and more convenient. Okay, so that's all for my presentation. Thank you very much. Thank you very much.